Hi, in this recording, I want to show you an alternate method to solving partial fraction decomposition other than setting up an algebraic equation, a system of algebraic equations and solving them. So let's take, for example, this integral of 9x minus 39 divided by the quantity x minus 3 times x plus 1 times x minus 5. We're integrating with respect to x, and we notice we have a polynomial divided by a polynomial, and so that clues us into the fact that we want to use partial fractions to decompose this and then integrate. So I'm just going to highlight that we're going to use partial fractions. And our first initial setup is to take and break up that initial rational expression into smaller fractions that are added up. So let me do a quick think bubble here. We are going to take 9x minus 39, and we want to divide it over x minus 3, x plus 1, and x minus 5. And that polynomial in the denominator is nicely factored for us, setting us up for our method. And we want to divide that up into separate smaller fractions. To do so, we take those factors in the denominator and we separate them into three distinct fractions. So I'll put x minus 3 under the first fraction, x plus 1 under the second, and x minus 5 under the third. And then in the numerator, remember, we have to put a value that is 1 degree less, or an expression that is 1 degree less than the denominator, and therefore I need to put constants or values a, b, and c in the numerator. Now, normally what we do now is we get a least common denominator and we add them up. So this first expression, a over x minus 3, would have to get multiplied by x plus 1 and x minus 5 if I want to get a common denominator. The next one is going to have to get multiplied. B is going to have to be multiplied by x minus 3 and x minus 5. And c would have to be multiplied by x minus 3 and x plus 1. And we do this both on the denominator and the numerator, right? So we would also be multiplying each denominator by those missing factors in order to get the common denominator that we seek, which is just, so let me write this down again, 9x minus 39 divided by x minus 3 times x plus 1 times x minus 5. And that's going to equal a times x plus 1 times x minus 5 all over that common denominator, x minus 3 times x plus 1 times x minus 5. And all of the fractions are going to have that same denominator, correct? So we can add them up, and let me just proceed. That's going to give us plus b times x minus 3 times x minus 5 plus c times x minus 3 times x plus 1. So this would be our first step in our partial fraction decomposition. Now notice, this is long. This is 3 fractions we have to add up. So now what do? Well, normally we would go ahead and we would multiply through right here and we would FOIL. And so after that foiling step, we would get 9x minus 39 over x minus 3 times x plus 1 times x minus 5. And then we would FOIL this out. So if you're okay, I'm going to skip some steps in here, and I'm just going to FOIL it out in my head where I multiply it through. B would get multiplied. Again, I'm going to skip some steps in here, and I'm just going to multiply this through in my head. And then C would get multiplied, and again, I'm going to skip some steps here and multiply that through in my head. And so, wow. So far, so good, right? So now we have, in fact, gone on and continued through this process of partial fractions. All right, so our next step, what's our next step? So in class, we've been talking about how if we have the same denominator on one side and the same denominator on the other side, we can ignore those denominators and simply equate the numerators. So I'm going to take 9x minus 39 and I'm going to equate it to the other side. And when doing so, I'm actually going to do, again, I'm going to drop a couple steps here. I'm going to combine like terms. The x squareds are all going to get together, meaning if I was to use distributive property and distribute the a, b, and c through to each trinomial, and then I combined like terms, for instance, you would see that you have an ax squared plus a bx squared plus a cx squared. And so I am skipping putting those all together, and I'm simply going to factor out an x squared and then write the coefficients next to it, a plus b plus c. I'm going to do the same thing with my x terms, right? I would normally have a minus 4ax, a minus 8bx, and a minus 2cx. And again, I could take out my x, and I'd be left with the coefficients minus 4,8, minus 8b, minus 2c. And then finally, I have all my constants, which I could lump together, which would be minus 5a plus 15b minus 3c. Phew. Okay, so when we've got three fractions we're adding up, the process is a little more difficult than when we just had two, correct? Well, let's keep going. So now at this point, what would we do? We would look at our coefficients. So a plus b plus c is the coefficient on x squared term. Negative 4a minus 8b minus 2c is the coefficient on the x term. And negative 5a plus 15b minus 3c, well, that's simply my constant, correct? So this is my constant. This middle one is the coefficient on x. And the first one is the coefficient of x squared. Because both sides of this equation are expressions and they're equivalent, they're equal, I can then look at the left side and make them match, equate those coefficients. Let's start at the back end. The constant is negative 39. So I know that negative 39 is equal to negative 5a plus 15b minus 3c. That has to equal the constant, negative 39. The coefficient on x is 9. So that means negative 4a minus 8b minus 2c is 9. And finally, a plus b plus c, which is the coefficient on x squared, well, there is no x squared here, right? It's as if there was 0 x squareds, and so that has to equal 0. And what that creates is a system of three equations with three unknowns, a, b, and c, and it is solvable, and we would then have to go on and solve. Lots of ways to solve. We could use matrices, I tend to put two equations together, eliminate a variable, put another two together, eliminate the same variable, and then solve the resulting system of two equations. But then we would have to actually just solve. So I'm just going to write down, we would solve the system of equations. Now, generally, if you have two equations, it's not that long of a process. But when you have three equations and sometimes more, it gets difficult. So there is an alternative way to work with partial fractions that kind of skips the step of having to solve the system of equations. And that's what I kind of want to go over now. All right, where to begin with this alternative method? Well, let's put this thought bubble in a thought bubble, okay, and keep this separate. There's nothing wrong with solving this way. It's just a little longer. So let's take a look at a shortcut. We have the same integral that we want to start with, and we separate that initial 9x minus 39 over x minus 3 times x plus 1 times x minus 5, just as before, and we write it as three fractions, where we put a constant over x minus 3, a constant over x plus 1, and a constant over x minus 5. we go about the process again as before, where we find the least common denominator, and so we're going to have to multiply the first one by x plus 1, x minus 5. The second one by x minus 3, x minus 5. And the third one by x minus 3, x plus 1. But this time, all right, well, slow down, Tina. You're going a little fast here. So what does that mean? That means 9x minus 39 over x minus 3 times x plus 1 times x minus 5 is equal to A times x plus 1 times x minus 5 plus B times x minus 3 times x minus 5 plus C times x minus 3 times x plus 1. And that's all over x minus 3 times x plus 1 times x minus 5. No changes, everything's the same. Similarly, we note we have a common denominator right here on both sides. Both denominators match, and therefore, in the same fashion, both numerators must match, and that means 9x minus 39 equals A times x plus 1 times x minus 5 plus B times x minus 5 times x minus 3, sorry about that, plus C times x minus 3 times x plus 1. And that is where the similarity ends, okay? For instead of equating our coefficients at this point, we want to diverge and do something a little different. What would happen if I was to look at this equation and say, suppose I let x equal the number 5 in that equation? Well, then I would have 9 times 5 minus 39 on the left side. But because it's an equation, I'd have to also plug 5 in on the right side, right? But if I let my x equal 5, what do you notice happens? I would have A times 5 plus 1, which is 6, times 5 minus 5, which actually turns out to be 0, right? And 0 times anything is 0, and that means that entire term would drop out. My A would drop out. Well, not only would A drop out, but notice x is 5, and so I would also be replacing 5 here in this second quantity. And again, notice 5 minus 5 is 0. 0 times B, this whole term drops out here as well, leaving us with simply that last term, which is C term in that equation on that side, which is C times 5 minus 3 times 5 plus 1. But what it does, notice this, is it leaves us with an equation with only a single variable, C times 2 times 6. And when you have an equation with a single variable to solve, you can solve that equation. Is that not sweet or what? 9 times 5 is 45. 45 minus 39 is 6. C times 2 times 6 is C times 12. And so that means 6 divided by 12 is C. Or in other words, C is just 1/2. Wow. Pretty cool, isn't it? Let's see if we can't do a similar thing, and let's see if we can't find A and B as well. Well, let me again try and drop a term out. So let me, in this time, I'm going to focus here. I want to let x equal -1. Okay, so I'm going to let x equal -1. On the left side, I have -9 minus 39. And on the right side, notice I'm going to just kind of drop a couple things. That's going to be 0 times -6. So that term is going to drop out, right? Letting x equal -1 gives us plus b times negative 6 times negative 4 plus c times, and see that last term here, that's going to give me negative 4 times 0, so that term is also going to drop out. And so really what I have is negative 9 minus 39, or negative 48, equals, and b times 24 is 24b. It looks like this time I get negative 48 divided by 24, which is negative 2. So it looks like my b value is actually negative 2. Ha! So I'm avoiding solving that algebraic system of equations, which would give us the same answer, but I'm doing it a little more creatively, right? I'm just plugging numbers in, and it's getting me quicker to the solution for A, B, and C. All right, what number do I want to pick last? So I have C, I have B. What am I looking for? I am now looking for A. So that means I don't want to cancel anything out here, but I want to cancel something from C and B. So notice this time I'm going to choose 3. I'm going to let x equal 3. That means on the left side, I have 9 times 3, or 27 minus 39. And on the right side, I have A times 3 plus 1 is 4, 3 minus 5 is negative 2, plus B times, again, this isn't going to matter, but 3 minus 5 is negative 2 times 0, because I've pre-designed it, so this term drops out. And plus C times 3 minus 3 is 0, times 4, but again, that term will drop out, leaving us with just A. 27 minus 39 is negative 6. Negative 6 equals A times negative 8, and therefore negative 6 divided by negative 8. Or if we like, what goes into that? 3/4? 3/4 is A. I want to stop there. I think I made a math mistake. I did. Hang on. Do you see that? I should have caught myself right here. Made a little math mistake. I do that with 9s and 7s. Do you do that? I'm just going to put a little smiley face saying, uh-oh. I thought it was wrong when I was doing that because I knew what. Anyways, let's try this one more time. 27 minus 39. That is not negative 6, right? Nope. Instead, what is that? Negative 12? 27, yeah, negative 12. Okay, that's a little better. Equals A times negative 8. And negative 12 divided by negative 8, that's just going to be 3/2. And so my A value is 3/2. All right, so I have now achieved finding my A, B, and C, just as I would if I had solved this long system of equations. But that's going to take a page. It really is. That sucker's, well, maybe not a whole page, but there's a likelihood that I'm going to make some mistakes over there. A lot of students tend to like this other method here that I just presented to get your coefficients. The idea of setting up your equations and then plugging in values strategically so that you can isolate for one variable at a time. But in either case, in either method, once we get our A, B, and C, we can now complete our integral. Remember, the whole process of partial fractions is done on the front end, where you use algebra and your brain in order to break up your original rational expression into smaller fractions or smaller rational expressions. So let's go back to the very beginning. Let's rewrite our integral, and let's remember our numbers. 1/2 for C, -2 for B, and 3/2 for A. And let me go here and let's solve this integral out. All right, so we've got all the way down to the bottom. Okay, so actually, hang on, I'm running out of space. So I think what I'm going to do, give me a sec, is I'm going to erase a little bit in here because we're all done with this and everybody's okay if I erase this in here, right? All right, and I'll take this away. And what were we doing here? We were finding an integral. Remember, we were taking an integral and we were rewriting that integral in terms of smaller fractions. And in place of a, we were putting 3/2. So I am going to erase a and I am going to instead write 3/2. In place of b, we are putting -2. So I'm going to erase b and instead I'm going to put -2. And in place of c, I had 1/2 for c. Are you happy? I'm super happy because we can solve each of these very quickly. Now we've been practicing this in class. So let me just erase a little more. I'm going to skip a bunch of steps again because we have been practicing in this. First of all, that 3/2 over x minus 3, if you like, you can treat it as a multiplication. A lot of students like to do it, me included, where I bring the 3/2 in front and that allows me to see what's left over. I also like to take those 3 terms and break them up into separate integrals. That would allow you, if you so choose, to do the direct u substitution and write out all your steps. So I would have the integral of 3/2 times 1 over x minus 3 plus the integral of -2 times 1 over x plus 1 plus the integral of 1/2 times 1 over x minus 5. As I mentioned, we could do a quick u sub. You could let u equal x minus 3. du is dx, just like we did in class, and then that's going to give you the integral of 3/2 times 1 over u du, which we know is just 3/2 times the natural log of the absolute value of u, which is just 3/2 times the natural log of x minus 3. And you could proceed and use the u substitution all the way through, or you can just jump to the chase all the way to the end and say, oh, hey, I understand how to do that u sub. I know what to do. I can do this in my head. I can go straight to my final answer, Tina. This is 3/2. Now, be careful though, right? We want to be careful. We want to make sure, I was just going to stop ourselves. I mean, we love making shortcuts, but we have to make sure we truly understand where it's coming from in order to create that shortcut. Don't just jump a shortcut without understanding where it's coming from, okay? So if you don't understand, then go through and make that u substitution to make sure you know where all the pieces come from. The next one, I do know where it all comes from, and so I'm going to skip and write that as -2 times the natural log of x plus 1. And the last one, 1/2 times the natural log of x minus 5. Once we did that basic part of getting our simpler fractions, then integrating became literally a 2-step process. That is our final answer. Okay, I hope this helps. I wanted to show you a different method to the alternative method that we had been working on in class, and that is simply taking and using numbers to get rid of and simplify down to get our A, B's, and C's as opposed to algebra. If you have any questions at all, please don't hesitate to reach out. Good luck, everybody.